If you work with computers, you've likely heard terms like RAM, hard drive, and processor mentioned by tech support or others who are more interested in what goes on inside of a computer's case. If you've always wondered what the various components of your computer are for, but have never really had the time to look into it, then this video is just for you. While each one of these components is complex enough to spend a lifetime learning about, I'm going to give a very broad and general overview. A typical desktop computer comes down to these 7 essential parts: case, power supply, motherboard, CPU, RAM, hard drive, and graphics cards. These are the fundamental parts of any desktop computer. It may seem daunting at first, so let's separate these into 2 categories: simple ones and the more complex ones. For starters, let's look at the case. The case is nothing more than a big hunk of plastic that houses everything else. Some of them have more or less physical space, some of them have different parts where you can put screws in or this or that, but at the end of the day, all the case really does is provide a nice enclosed system for everything else. Next up, we have the power supply. This part of your computer, almost always located on the bottom, is the part that plugs into the wall and provides all of the other parts with the electricity needed to do their thing. You can think of it as an extremely advanced AC adapter. The last of the simple parts to mention is the motherboard. The motherboard is a wide and flat circuit board that all of the other components plug into. It's the part that lets all of these components send electrical currents, composing data, between each other. While not particularly expensive, the motherboard is arguably the most important component because without it, you'd have nowhere to put anything else. So that's it for the simple components. Now let's move on to the more complex parts, the ones that deal with data. The 4 main components to keep in mind here are CPU, RAM, hard drive, and graphics card. Now first things first, I'm going to establish some terminology. Keep in mind that CPU is also known as the Central Processing Unit, or processor. These terms all refer to the same thing. They are completely interchangeable. RAM stands for Random Access Memory and is often referred to as just memory. A hard drive is often referred to as a disk drive or storage. And a graphics card is also known as a GPU or graphics processing unit. For this explanation, I'll be using the terms CPU, RAM, hard drive, and graphics card. So let's start with the CPU. The CPU is where your computer does things. It isn't really capable of storing very much data at all, but it's very good at doing things with data. Quickly reading it, arranging it, doing the type of quick and massive calculations needed to run your programs. This is where most of your programs are essentially run from. It's often referred to as the brain of the computer. I personally don't like this description because really your entire computer is just a brain. It's just the center part of your computer's brain. Basically everything that happens in your computer goes through your CPU at some point. Now let's talk about RAM and hard drive at the same time because they have a very unique relationship, which is probably why people often confuse the two. Your hard drive is where all of your data is stored. When your computer tells you you're running low on space, it's because your hard drive is almost full. All of the data that makes up your videos, pictures, documents, project files, or the 3D worlds and models that make up a game are all stored here. While hard drives can store lots of data, they're relatively bad at accessing that data quickly. Everything is accessed through a tiny little wire here, and because most hard drives are made up of spinning disks, your hard drive isn't going to be able to constantly give your CPU the information it needs to run certain programs. That's where RAM comes in. RAM is another form of storage. It stores the exact same kind of data as your hard drive, but RAM sacrifices storage space for nearly instant accessibility. Unlike your hard drive, which sends all of its data through a tiny little thin wire, your RAM is arranged in these long, thin sticks that insert into your motherboard. Think about a storage unit. If you have a massive warehouse with only a thin doorway, it's going to be difficult to get in, find what you need, and get out if it's kind of spread all over the place. You'll have to go through a tiny door. But if you have a long, wide storage shed that's got a big, massive garage composing an entire side of it, you won't be able to store as much, but things are significantly easier to get to. Typically, if your computer has 1,000 gigabytes of storage space in your hard drive, it's likely got about 16 gigabytes worth of RAM. Here's where you put the stuff you own but you aren't currently using, And this smaller one is where you put the stuff that you are using and need to be able to get in and out of quickly. When you run a program or a project file, your CPU identifies what parts of data are needed for that program to run. It pulls them from your hard drive, and then it stores them in your RAM sticks for quick accessibility. This is why when you start a new level of a game, for instance, it has to load. Anytime you see loading, it's loading the data that composes that level from your bulky hard drive into your RAM. From a user's perspective, just follow this rule of thumb. RAM allows you to run intensive programs, while disk space allows you to have more of these programs installed. It also allows you to have more of the data they're referencing, whether it be pictures, videos, or mods. And finally, we get to the graphics card. With all of the calculations going on in your computer to turn a bunch of numbers that basically come down to ones and zeros into a constantly updated three-dimensional world, the final and most important and arguably most difficult step is to display that on your monitor. It's possible for your motherboard to do this alone, but it's not going to look good, and it's certainly not going to be able to do much. Your graphics card is essentially an entire computer in and of itself, dedicated to the sole task of figuring out what pixels need to light up on your screen, in what color, and at what time. If you were playing a game that had a very busy and high texture world with lots of models and different angles and colors, your CPU is the thing that creates that world. It knows where the stuff is, and it does so with data that's been stored in your RAM, which was loaded out of your hard drive, but it's your graphics card that figures out what it's supposed to look like based on where you're standing in the world. Without getting too off topic here, if you're somebody who likes math, I highly recommend you look up fast inverse square root, which is directly related to how three-dimensional worlds calculate perspectives. So that pretty much sums it up. There are other components worth mentioning, such as cooling systems or internal wireless cards, but really those are extras. So to summarize what I talked about so far, the case stores everything in a physical box, the power supply gives electricity to what needs it, the motherboard is the body that everything plugs into, the CPU does everything, RAM stores data that is needed for quick access, hard drives store everything that you have installed and the data that goes along with those programs, while the graphics card figures out how it's all supposed to look on your monitor. Well, thank you very much for watching. I hope I helped, and if you have any questions, feel free to leave a comment and I'll do my best to answer them. In order for your computer to figure out which of your monitor's pixels should be what color at what time on your screen within a matter of milliseconds, it has to do a ton of calculations very, very quickly. In modern computers, this is accomplished by the graphics card, a term many are familiar with, but might not understand all that well. Now, a graphics card is like a smaller version of your entire computer, but one dedicated to the task of figuring out how to put images on your screen, particularly images that represent a three-dimensional world. Like your computer, the graphics card has its own processor inside of it, known as the GPU, or Graphics Processing Unit. The GPU is to your graphics card what the CPU is to your computer as a whole. The primary difference between a GPU and a CPU is in how many cores they have. The cores of a processor are like small calculators that can very quickly do the calculations required for your computer to think. A modern CPU usually has about 8 cores at least, while a modern graphics card has anywhere between 1,000 and 4,000 of them. Although a CPU has less cores, each core in the CPU is far more powerful than each one in the graphics card. This is because CPUs are used for things like logic and instructions, which can get very complicated. Even though these cores are more powerful, they can each only do one task at a time. Now, when you're talking about instructions, that's okay. But the individual tasks that are required for graphics rendering aren't really all that complicated, there's just a lot of them. So using a CPU to render graphics would result in all of the potential of those cores being wasted. We end up with all the tasks waiting in line and being rendered slowly. Not ideal for graphics. Now, the cores in a graphics processing unit, being simple but very numerous, are perfect for this task. So in summary, a CPU can do 8 really complicated things at once, while a GPU can do thousands of very simple things at once. Think of one person with 2 big strong arms and another person with 10 very weak arms. If you needed 2 big heavy things lifted, the guy with 2 arms is best for that task. But if you need 10 lightweight things lifted, someone with 10 weak arms is better. The ability to do a bunch of calculations quickly is particularly important for the rendering of three-dimensional worlds. When computers create 3D worlds, they use something called vector graphics. This means they plot out the coordinates on a three-dimensional graph and then draw lines in between them based off mathematical calculations, similar to what you likely did in geometry class. Every object and shape really just comes down to that. Where are these points in relation to each other, and what is the curvature of the line between them? That all just comes down to math, doing a whole bunch of calculations really quickly. This is also why graphics cards are so useful in the process of acquiring cryptocurrency. The type of calculations needed to participate in what's known as Bitcoin mining are far more suited to a bunch of small cores than a few very powerful ones. Now, because your graphics card is like its own computer, it not only has its own CPU, but it also has its own RAM. This is often referred to as video RAM or VRAM. And like with your computer's primary RAM, the RAM in your graphics card stores small amounts of very easily accessible data. In the image creation process, some types of data are very important and need to be used regularly, so the RAM in your graphics card stores that data and sends it to the GPU as needed. So those are the basics of why and how a graphics card does what it does. In my recent video on binary, I explained how two-state transistors are used to represent binary numbers composing data. In this video, I will explain a different way that binary data is stored, which is on a spinning disk drive. Now, if you haven't seen my video on binary, or if you don't exactly know how binary works, it might help to check that video out after this one to give you some context. So we know that computer data is all stored in binary, something that can have two states, which is interpreted as a 1 or a 0. How does a spinning disk achieve this, and what advantages does a spinning disk have over the microtransistor method? The answer to how is essentially just with magnets. The spinning disk in your hard drive contains what is known as ferromagnetic material. Put simply, that means it can be magnetically charged. Your hard drive is divided into billions of tiny little magnetic regions. Each magnetic region can have its polarity changed to be positive or negative. Therefore, a single region is used to represent a single digit of binary. Typically, a positive charge represents a 1, while a negative charge represents a 0. The disk is placed on a central spindle. The spindle spins around, causing the disk to spin around. Meanwhile, an actuator arm is placed on top of the disk, not even a millimeter away from it. This arm has the ability to send very subtle magnetic charges to the disk and the ability to interpret the ones that are already there. This is known as reading and writing information. When you install a program or download a picture to your computer's hard drive, the actuator arm leaves a long pattern of charges along the spinning disk. That's writing information. When you run said program or load said picture, the actuator goes back to where it put that pattern of magnetic charges, interprets it, and sends it back to your CPU or RAM or wherever it's needed for quick access. This is the reading process. Before moving on, I'd like to make a side note here. It's worth mentioning just a few things. Modern hard drives have multiple spinning disks, each with their own actuator arm. Additionally, a disk can have information stored on either side of it, so each disk has an actuator arm for both sides. Lastly, many modern hard drives have a different part of the actuator arm read and write, allowing things to be loaded from and onto the drive at the same time. Now we know how data is stored on and read from a spinning disk. But with all of the files and programs stored on your hard drive, how does it know where physically on your hard drive it's stored that pattern of magnetic charges? The hard drive has two methods of doing this. One is with what is known as a cache, the other is with what is known as a file allocation table. First, let's talk about the file allocation table. The disk of a hard drive is divided into several different organizational areas. We mentioned regions are the small tiny parts that each represent a digit of binary. Now, tracks are essentially concentric rings around the drive which the regions can be stored on. Each track is divided into segments called sectors, and multiple sectors are grouped into what's called a cluster. Whenever you install a program or store data on a disk, the write head on the actuator arm stores the data there and then immediately afterwards writes a smaller, easier to access piece of data, letting it know generally which track and cluster it stored the data on. Later, when you go to load that data back up, the reader head first checks the file allocation table to figure out where to go, and then goes there to find the specific piece of data you're looking for and read it. Now let's talk about the cache. This works very similarly to the file allocation table, but with a significantly more precise map to where that data was stored, therefore resulting in significantly faster loading times. A cache can be stored on the hard drive itself, in your RAM, or even in the CPU. Caches are made when your computer identifies information that needs to be accessed very quickly and very frequently, such as if you imported a video file into a video editing program or a photo into Photoshop. The data is still stored on your hard drive, but because your CPU has a cache knowing exactly where on the hard drive it is, it can be accessed and loaded into RAM very quickly. So that pretty much wraps up the fundamentals of how a hard drive stores data. Now let's address the question of why. Why use something that is essentially a hyper-advanced record player when we have solid-state technology? All the other binary data in your computer is stored using microtransistors, small switches that don't move and can be accessed much faster without having to wait for a spinning disk to finish a revolution. Well, what disk drives lack in speed, they make up for in space. As small as microtransistors are, they don't compare to the magnetically charged regions on a disk drive. And while microtransistors get smaller every year, so do these magnetic regions. Currently, the average solid-state hard drives have about a 500 gigabyte capacity. For the same price, you can get a spinning disk hard drive that will have about a 3000 gigabyte capacity. The optimal setup for a modern computer is to have a solid-state drive for your operating system and programs to be installed on, and then have a large capacity spinning disk drive to have all the data that those programs reference stored on. I personally have a 500 gigabyte solid state drive that excels in speed, which I run my operating system and my programs from, and 3 spinning disk hard drives, each with about a 3000 gig capacity, which I store all my data on. You've likely heard somebody suggest defragmentation as a solution to a hard drive that's running out of space or loading certain things unusually slow. To give a quick refresher on how your hard drive stores data, a sequence of positive and negative electrical charges on the disk represent binary code, and an actuator arm is used to read and write these charges, which is loading the data to and from the rest of our computer. Other parts of the hard drive, such as the file allocation table, are used to keep track of where all these things were placed. So now let's talk about the concept of fragmentation by looking at an example. Imagine this black line is one of the tracks on my hard drive's disks. That's where these sequences of charges are stored. Now let's say I download a large file, like a movie, onto my hard drive. This red section here is the physical sequence of charges that makes the data on my disk where that movie is stored. And then I download 2 other movies, the blue one and then the green one. The actuator arm puts one sequence of data after the other, and it remembers where they are. No problems here, this is all fine. But then later, I delete the second movie I downloaded, leaving this blank space in between these 2. And then I download a 4th, much larger movie. My hard drive has empty space here, and it wants to utilize it, but it's not enough to fit the entire movie I want to download. It doesn't want that space to go to waste though. So it puts half of the movie here, and half of it on the other side. This is now a fragmented file. It'll still work just fine once it's been loaded into my RAM, but it's going to take a little bit longer to do so, and it will also require more data on the file allocation table to keep track of where it is. Now, this is a very simple example. As you delete and add more files or more programs to a hard drive over time, this fragmentation can get really bad, leading to long load times and a lot of wasted space, keeping track of how all this stuff is scattered about. When you run a defragmenter, your hard drive, with the help of your RAM and CPU, goes through all these messy cut-up files and then puts them together where they belong. Think of the shelves of a grocery store. On one aisle, you have the beans, and then in a separate aisle, you'll have bread, and then in another, you have frozen foods. And you have convenient signs above them letting you know where each of these things is. If the cans of beans, frozen foods, and bread were all just randomly scattered throughout the store's aisles, sure, the store would have the same amount of these things as if it were organized, but you'd have to run all over the place to find them, and you need a complicated list indexing where all of it's located. That's a fragmented hard drive. I mentioned in my video on computer components what RAM is and the role that it plays. In this video, I will be going a bit more in depth into this component, explaining precisely what, why, and how it does what it does by going into the 2 main subcategories of RAM, dynamic RAM and static RAM. To give a brief refresher, RAM is a bit of a middle ground. Hard drives are very slow but store a ton of data, while processors are extremely fast but store hardly any data. Random access memory is a mixture of the two, a place for large, bulky data and machine code to be temporarily stored so your CPU can grab it and use it faster than the hard drive would be able to provide for it. So let's take a look at the two types of RAM, static RAM and dynamic RAM, often referred to as SRAM and DRAM respectively. Every stick of RAM that you buy is going to have a little bit of both, as they're intended to work synergistically. Here are the main differences between the two from a functional perspective. Static RAM stores less data, while dynamic RAM stores more. Static RAM can be accessed much faster, and dynamic RAM can be changed much faster. Dynamic RAM costs less, and dynamic RAM uses more power. Now let's talk about how each of these work, and then I'll get into the types of things each one is used for. Dynamic RAM stores binary data by using one transistor and one capacitor for each bit. As I mentioned in my video on binary, this code of ones and zeros is what all data and instructions come down to. In dynamic RAM, if a capacitor is holding a charge, it's a 1, and if not, it's a 0. The transistor connected to this capacitor lets the rest of your computer know if the capacitor is charged or not, and it also allows it to be changed as requested. Think of the transistor as what controls what is stored, while the capacitor is where it is stored. The advantages of this are that the transistor and capacitor put together are incredibly small, allowing for millions of them to be present in an area the size of your finger. The problem with microcapacitors is that they lose their charge very quickly. They can only store it for a few milliseconds, and this means that in order to remain charged,
my friends like photobombing a lot. They just like to just bring their heads in, their fingers.
The capacitor must constantly be refreshed with tiny bits of electrical current. This results in memory that can't be accessed quite as fast as it could if it were in a constant state. But because this type of memory is constantly refreshed anyways, it makes it easier to make changes in its state from on to off. Now let's take a look at how static memory works. Instead of using capacitors, static memory uses only transistors. But it requires 4 or sometimes 6 of them in order to represent one single digit of binary, and therefore one bit of data. Static RAM accomplishes this by using something called the Boolean method, which is too complex to get into now, but I'll make a video on it in the future. In short, because static RAM requires more transistors to represent a single bit of information, it obviously requires more physical space on your RAM chips in order to do so. This results in less storage space. The advantages of this method is that unlike capacitors, static memory is constantly in the state that it's in. Whether it's representing a 1 or a 0, it remains that way and can be read that way until it's told to change. And this means that it can be accessed much faster than dynamic RAM, which sometimes has to wait for a refresh before it can be read. So we have a high capacity, easy to change, but somewhat slow system of memory, and a low capacity, harder to change but instantly readable system of memory. Why are both necessary, and when is one used rather than the other? As you may have guessed, static RAM is used to store data or instructions that aren't particularly large but need to be accessed frequently and quickly, such as a cache. Meanwhile, dynamic RAM is used for everything else. Things that aren't needed quite as urgently or frequently, but take up more space. In a way, static RAM does for your RAM what RAM does for your computer as a whole. Low storage, but fast and reliable access. Meanwhile, dynamic RAM does for your RAM what a hard drive does for your computer. It's not as quickly accessible, but it has far more storage. It's hard to give specific examples of when one is used rather than the other because the difference is determined by very, very low-level operations, things that a typical user isn't really going to have any experience with. Just keep in mind that both are very important for your computer's functionality. When we interact with computers, we're mainly looking at the screens. Tens and thousands of tiny little pixels that can light up in certain colors and change to create the images we see and interact with. So with a computer that can only think in numbers, how does the computer decide which pixel is supposed to be what color and at what time? Well, if you want to know, then you're in the right place. The colors that make up each individual pixel in your monitor are created with various compositions of the RGB color scheme. A certain amount of red, green, and blue with different amounts of each can create any color with any shade of any saturation, darkness, or lightness. Whenever you see the term RGB, this is what it's referring to: colors based off of combinations of red, green, and blue. Before we get to the numbers and software part of this, let's briefly talk about the physical component of how pixels work. There are actually quite a few different ways this is accomplished, and various methods have been used over the past few decades. I'm going to skip over CRT monitors because they're vastly outdated and function in a very different way than the other two types of monitors I want to talk about. Nevertheless, these monitors are very interesting, so I encourage you to look into how they work. There's really brilliant technology in these monitors. Let's start with LCD or liquid crystal display monitors. At the very back of these monitors is a white fluorescent light covered by a few thin layers of a unique substance known as liquid crystalline. On each side of this layer of liquid crystalline is a layer of polarizing filament, one negatively charged and the other positively charged. Now, because white light is the presence of all colors, the layers in front of this white light filter out the colors needed for each pixel. Each pixel on these filter screens has its frequency charged by electrical signals coming from the top and sides, causing it to let through a different color at a different time. Now, the second common type of monitor these days is the LED monitor, or light emitting diode. This works similarly to the LCD display, but instead of a single white fluorescent light at the back, it has a layer of LED pixels. Inside each pixel are 3 small LED lights, one dedicated to each color of the RGB spectrum. Of course, with various wavelengths being applied to each, the final color of the pixel is determined through a combination of the 3. While it may seem to be a problem that the lights inside each pixel might not be equally spaced depending on which colors are adjacent to others, when we zoom out and look at thousands of pixels on the screen, our eyes naturally blur them together as needed. So now that we've established the physical side of this, let's move on to the numbers. Each red, green, and blue value has 255 different shades it can be, on a scale of black to the color in question. There are millions of different ways to combine each of these 3 numbers, and as a result, millions of possible colors we can represent. But while it's represented this way here, your computer isn't using 3 values of 255 to do this. Instead, it's using one single number that it reads in a very specific way. To figure out how a computer turns a number into a color, we need to first look briefly at what hexadecimal is. I've spoken in recent videos about binary and base 10. Base 10 is the counting system we've all used. We have the numbers 0 through 9, and once we get to 9, we add a digit to the left and flip the previous digit back to 0 and start over. Whenever all of the digits to the right are full, we add another digit to the left. Hexadecimal works the same way, but instead of having 10 values for each digit, as in decimal, or 2, as in binary, it has 16 symbols for each digit. This means that each digit to the left we add is an increasing power of 16 rather than one of 10. In our normal system, called decimal or base 10, this is the number of ones we have, this is the number of tens we have, this is the number of hundreds, the number of thousands, 10,000s, and so on. In hexadecimal, this first column is the number of ones we have, the second is the number of 16s, this is the number of 256s, the number of 4096s, and so on. Because we only have the digits 0 through 9, hexadecimal represents the numbers 10 through 15 by using uppercase letters. So counting up past 9 in hexadecimal would sound like 7, 8, 9, A, B, C, D, E, F, and then we add 1 to the left column and start again from 0. Hexadecimal is very common in computers because it relates well to binary. More on that later, but for now, let's talk about how does this turn into
This might just be the easiest way to make money online. For example, Jason is making anything up to
colors. Each pixel has these 3 colors, each represented by a number between 0 and 255, and as luck would have it, 2 digits of hexadecimal can also represent any number between 0 and 255. So each pixel on your screen has 6 digits of hexadecimal dedicated to it. With 6 digits of hexadecimal, we can represent any number from 0 to 16,777,215. Each individual value of this number is interpreted by your monitor as a different color, so each pixel reads that hexadecimal number and can become any number between those. Now going back to RGB, every 2 digits of this 6-digit hexadecimal number are dedicated to one of the RGB colors. The first 2 digits are used to determine the amount of blue, the second 2 are used to determine the amount of green, and the final 2 are used to determine the amount of red. Notice that as I increase the various values, their hexadecimal values scale very neatly within the rows of 2, while the equivalent decimal value sort of jumps all over the place. As human beings, we really like base 10 numbers, likely because we have 10 fingers. So why does this method of determining colors use something as strange as base 16? The reason for this is that computers actually have a fairly difficult time working with base 10. I talked in my video on binary, which can be found in the description, that everything computers do essentially comes down to numbers that use base 2. Now 16 is a power of 2, while 10 is not. So computers don't have much trouble converting numbers from base 2 into base 16, but have to go a bit out of their comfort zone to represent things in base 10. They can still do it incredibly fast, as you can see here, but when they have to calculate tens of thousands of pixels dozens of times a second and several other values, it's far more efficient for them to do it their way, which is with powers of 2. So that concludes the basics of how computers determine what colors to display on the screen. As always, I encourage you to dive into the massive amount of information available on this topic, especially when it comes to the cathode ray tube monitors, which again, I love and are such brilliant pieces of technology. It's a common theme throughout the modern world that everything in a computer's brain comes down to ones and zeros. You've most likely heard that this code of ones and zeros is what's referred to as binary, and while almost everybody knows that this is somehow related to what computers do, very few of us seem to understand what binary is or why computers use it. If you want to know, then this video is for you, because it's actually a very simple concept and still quite fascinating. Before we get to computers, let's talk about what binary itself is, as it existed long before computers did. Binary is nothing more than a system of counting. To understand how it works, let's look at 2 other systems of counting, tally marks and the glorious base 10 positional that we all know and love today. Tally marks are the simplest counting system imaginable. However many things you have, you put down that many marks, easy as pie, but not very efficient. Meanwhile, base 10 positional, which is what we use today, uses a different symbol to represent different amounts of things. With the numbers 0 through 9, we can recognize that each symbol indicates a different amount of things. If we need to represent something higher than 9, we add a digit to the left, roll this first digit back to 0, and start over. This system is very efficient compared to tally marks because each digit we add exponentially increases the amount of things we can represent. Because in this system we add a new digit every 10 things, each digit represents an increasing power of 10. This is the number of ones we have, the number of tens, the number of hundreds, the number of thousands, and so on. Now this is probably something you already know, but it's very important to keep it in mind when we talk about binary. Now binary works the exact same way as base 10 positional, but instead of each digit going from 0 to 9, it goes from 0 to 1. Counting upwards in binary sounds like this: 0, 1, 10, 11, 100, 101, 110, 111, and 1000. Because each digit of binary has only 2 values and not 10, each additional digit represents an increasing power of 2 rather than an increasing power of 10. So this is the number of ones we have, the number of 2s, 4s, 8s, 16s, 32s, 64s, 128s, and so on. Not nearly as efficient as base 10, but exponentially more efficient than tally marks. Literally. So now that we know how binary works, let's talk about computers. Why did the first computer creators, as wise and intelligent as they are, waste their time with such an ineffective system of counting? Well, it's because of a physical limitation on how computers work. Everything a computer does comes down to what's known as microtransistors. Simple, tiny, eensy-beensy little switches that can either be on or off and can be flipped on or off with a very weak electrical charge. The first goal was to get computers to count, And to get them to count by using these switches, we could use the tally system, meaning the number of on switches equals the number of things we have, or we could use the much more efficient system of binary, where each switch represents a digit of binary. 8 transistors using the tally system could represent a number as large as 8 by turning all of them on. With binary, we can represent a number as high as 255. An on switch means a 1, and an off switch means a 0. Now is a good time to mention that a single transistor is what's known as a bit, which stands for binary digit. A byte is 8 of these bits in a row, which means any number between 0 and 255. So if binary is just a system of counting, what do people mean when they explain how to spell things in binary? Well, what they really mean is how to spell things with ASCII. The American Standard Code for Information Interchange is a way to convert a computer's data, which can only be in numbers, and turn it into letters for humans to have an easier time to work with. ASCII simply assigns a character to each value represented by a byte of binary. And because a byte has 8 digits of binary to work with, and 8 digits of binary can represent up to 255 values, ASCII had 255 letters and symbols to choose from, more than enough for the entire alphabet, punctuation marks, and other symbols. For example, the corresponding ASCII number for an uppercase A is 65. Now 65 in base 10 is equal to 1,000,001 in binary. So whenever you type in an uppercase A in a word program, a coding program, or a scripting program or whatever, somewhere there's a little tiny row of 8 transistors arranged in the pattern of off, on, off, 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 on, which represents 0, 1, 0, 0, 0, 0, 0, 1 in binary, which is interpreted as 65 in base 10, which is converted by ASCII into an uppercase A. You're likely starting to get a feel for the staggering amount.
Hello again. Well, you know all the hours you're spending trying to teach yourself a trade. 1 hour with me will help you skip most of the hours on your own, because I'm going to teach you how to do it professionally in less than 30 minutes a day. This is a complete system. It will find the trades, it will show you how to place them, and when I show you what I use, what I look for, and how I do everything, I'll bring 25 years of experience and a £5 million trading system of professionally tuned strategies that are simple to understand, and be able to show you how you can go through them all and pick winning trades. All you have to do, and this is your part, is register and
Of transistors required to write something as simple as a Facebook status, let alone all the different coding that your computer has to do to make the screen light up, play games, calculate massive values, and so on. Well, long before we got to the point where your phone can play 3-dimensional games, it became clear that numbers as high as 255 just weren't going to cut it. Regardless of how many bytes we had, and it was a lot, even adding 4 fully active bytes together could only get a number as high as 1020. To solve this problem, new computers were designed to recognize 2 bytes as one single number. So now, instead of referencing 1 line of 8 transistors, computers could reference 2 lines, giving 16 digits worth of binary. This was a huge help because it increased the amount of representable numbers exponentially from 255 up to 65,535. When you hear people talking about the difference between 8-bit and 16-bit, this is more or less it. Now that doesn't mean that a 16-bit system is exponentially that much more powerful, because your program isn't always going to be utilizing all of these numbers in each byte that it represents. It just has the option to, which opens up lots of doors. In the video I made on binary, I explained why it is that computers use ones and zeros to think. The ones and zeros represent the state of a single electrical cell inside the computer, which can be one of 2 states. But is this the only way of doing it, or are there other options that let us work with more than just 2 states? Well, actually, yes, there are. And in the early years of computer engineering, people experimented with computers that could use base 3, base 8, base 10, and even base 16. So why were these methods abandoned in favor of binary? If you want to know, then this video is just for you. So to clarify one thing, when we refer to a transistor being on or off, What we really mean is that it's either a high charge or low charge, respectively. An on cell has a very high amount of electricity stored in it, or moving through it, while an off cell has a low amount. These states determine whether or not a single cell represents a 0 or a 1 in our binary code. So if a computer can read and write data to these cells by sensing or storing different amounts of electrical charge in each one, why can't we get more specific with them? What if, instead of less than 50% charge being a 0 and above 50% charge being a 1, we divided it into 4 segments, like this? Now, 0 to 25% charge could be a 0, 25 to 50% could be a 1, 50 to 75% could be a 2, and 75 to 100% could be a 3. With this method, each individual cell could have 4 states, meaning that each byte of data could be a number designed around base 4 instead of around base 2. Where a byte of 8 transistors could have 256 values with base 2, our new system could let us have 65,536 values with base 4. Way better, right? Better yet, what if each cell could represent 8 or 10 or 16 different states by making the bit even more precise? Well, as mentioned above, these methods were experimented with. The amount of states a single cell of information can hold is referred to as a logic level. Binary is called 2-level logic, and the one I just described would be known as 4-level logic. The fundamental problem with using logic levels greater than 2 to represent numbers is reliability. While computers are really good at storing and reading the electricity in each cell, the exact voltage tends to fluctuate a little bit. Take a look here. The sort of natural fluctuation of electricity means that the level of voltage in this cell of data wobbles off by, let's say, 20 percentage points. Even if things get really bad, like 40% off, we have a lot of leeway on either side. For an on state, we try to keep it at 100%, but if it falls every now and then, it's still above 50% and remains interpreted as a 1. But in our method of splitting into fourths, even the natural fluctuation of 20% gets dangerously close to crossing the line, and the higher the amount of states in each cell, the more specific this voltage has to be, and by extension, the more likely it is to be wrong. It's especially difficult to try to balance the voltage in the middle where it can't be too high or too low. When we only have 2 states, for off we can keep it as low as possible, and for high we can keep it as high as possible. We don't really have to worry about overshooting.